right? So let's start here. We're going to start at this one because this one is a simple tetrahedron, and then we'll be able to determine the configuration on this one a little bit easier than the other two. I'm going to show you a shortcut on the second example, and then the Fischer projection, we'll discuss that separately. All right, so what is configuration? Somebody help me out. What does that term refer to?
Do you want me to like explain how you get configuration?
No, just define it. What does it mean? When I say that a chiral center has a certain configuration, what does that mean?
It's like how it's built. That's its orientation.
Yeah. So how the it's referring to the 3D orientation of the groups, excuse me, around the chiral center. So the 3D orientation of the groups around the chiral center. Right, and for configuration, it can be, I mentioned this the other day, R or S, depending on how those groups are arranged. So let's look at that first example. And R is clockwise, S is counterclockwise. So CCW is counterclockwise, and then CW is clockwise. All right, clockwise will be going this way when we prioritize them and count them up, and then counterclockwise will be going the opposite direction. All right, so in order to determine configuration, there are a couple of steps we have to take, right? You saw it in the video, so we don't have to like really beat a dead horse, but we need to understand what we're looking for. So the first step is to prioritize your groups. Right, and priority is based on the atomic number. All right, and what we're looking at, because there's a temptation to add atoms together, add the atomic numbers together. We're not going to do that. What we're looking at is the first atom that's attached to the chiral center. All right, the first one. If the atoms are the same, like as you can see here, you have a carbon here, a carbon here, and a carbon here. Then we have to take another step and look at what's connected to that atom. But we'll talk about that in a second. So if we're comparing the carbons and oxygen, which one has the higher priority?
Oxygen.
Oxygen, good, right? The atomic number of oxygen is 16, if I'm not mistaken, compared to carbon, which is 12. So oxygen has the higher atomic number, so it has the highest priority. And priority is from 1 to 4, with 1 being the highest.
I have a question when you're done.
Go right ahead.
So for that example, is there only one chiral center?
Yes.
Okay.
Yeah, because if you look at the top carbon, it has 2 hydrogens on it. So that can't be a chiral center because it doesn't have 4 different groups. Okay. Look at this carbon, is sp2. So that can't be chiral because the chiral center has to be sp3. And then if you look at this carbon, that's sp. So that also can't be a chiral center.
Okay.
So the only chiral center here is, I didn't mean to erase my highlights, right here, that carbon. All right, so that's the only chiral center that's present. And so the priority, highest priority group is oxygen. All right, now let's compare the carbons, right? So if you look at this carbon right here, I'm gonna change the colors up. This carbon has a double bond to oxygen. This carbon up here, we erase these hydrogens because they're understood. as a single bond to oxygen. And then this carbon over here has a different color, sorry about that, has a triple bond to nitrogen. So when the atoms are the same, we have to move to the next atom. All right, so this carbon that's circled in red is bonded to nitrogen. The other two are bonded to oxygens. So between the two carbons that are bonded to oxygen and the one that is bonded to nitrogen, which one do you think is lower in priority?
The oxygen.
Okay, let's think about that. What's the atomic number of oxygen compared to nitrogen? Is it higher or lower?
Lower. Okay.
Oxygen is 16, nitrogen is 15.
Oh, it's higher.
Yeah. So this group is going to be lower in priority. You following that?
I thought if it was triple bonded, then you count it 3 times.
Only if you're comparing it to another atom bonded to the same atom. So if I was comparing it to another carbon bonded to nitrogen, then it would supersede the oxygen.
Oh.
Excuse me.
Okay.
You following that? So
Mhm.
if I was comparing the cyanide versus an ME,
Mhm.
following,
Mhm.
then this would be higher in priority because it has 3 bonds to nitrogen, where the other one has 2.
Okay.
But I'm comparing that to carbons that are bound to oxygen, and oxygen has a higher atomic number than nitrogen. So those groups that are bound to oxygen
Mhm.
are going to have higher priority than the carbon that's bound to nitrogen.
Okay.
All right. So that's going to be obviously 4. Following, because it's compared to the other 2, one of those is going to be 2, one's going to be 3. And so the nitrile group has to be 4. Any questions about that? Anybody not see that?
I have a question.
Go ahead.
So the hydroxide group connected to the carbon up top, that's 3.
Well, yeah, it will be when we compare it to the aldehyde, yes.
Mm,
Because we're comparing now these two. Excuse me. And when we look at those two carbons, one has a double bond to oxygen and one has a single bond to oxygen. So the one with the double bond is higher in priority.
Okay.
All right, so now this becomes 2. This group right here is 2. And then up top, that group is 3. Anybody not seeing that? Like how to assign the priority? I know it's kind of it may be new. We talked about it a little bit in part 2. I'm sorry, part 1. But when you're comparing atoms that are the same, you have to move to find a point of difference. So in this case, between what we have labeled as 2 and 3, one of those carbons is bound to oxygen once up top. And then this one has 2 bonds to oxygen. All right. So this is going to be higher in priority. All right. So once we prioritize, we can reorient so that we can get the top 3 groups facing us and the 4th group away from us. Right. So for this particular group, let me get the model. Let me pull a model up. I need to turn my video back on. All right. So for this particular group, we're going to say that the cyanide, since I'm going to try to keep them the same colors if I can. So the OH, I'm going to make black. carbonyl is purple. The top is blue. Come on, Russell, tighten up. All right, give me 1 second. Let me just finish building this. And then the cyanide is going to be red. OH is black, so that's that. So the way this looks, to you, the black atom is coming out at you. Turn my background off. Oh, no. So you can see the black atom is coming out at you. The carbonyl is going away from you. So that would be on a dash, that would be coming towards me. And then that top group is just on a vertical line. And then the cyanide would be here. Right? We're following that. So what would you do to only show the top 3 groups? What could you do here? If it's in this type of conformation where it's just a tetrahedral, the easiest thing to do is just put that, again, put the axis through here. Like that, and just rotate around it. Like that. So all you want to see is those top 3 groups. So what would that look like?
I have a question.
Go ahead.
So you said, so you can see the top 3 groups, but
Priority wise.
The red one is facing you. So
yes, it's away. So if it was on your side, it would be, you'd be looking at it from this direction, but because of the camera is backwards. So
okay.
yeah, but you want that 4th group away from you.
Oh, the 4th group away. Yeah. Oh,
top 3 groups coming out, 4th group away. It's called a steering wheel. So I'm just gonna put that here. And what was purple? Purple was 2. And then black was 1.
When you say the 4th group, do you mean the like the one that was
in priority, the lowest in priority?
Okay.
So you want the lowest priority group away from you.
Okay.
Right. So you want to look at it in what's called the steering wheel. So this is what that would look like. All right. So on the paper, you see how I have it drawn. All I care about is those top 3 groups. Is that clock, when I count to 3 here, is that going to be clockwise or counterclockwise?
Clockwise.
Clockwise.
Going that way, right? So what is the configuration of that stereocenter?
Is it R?
It's R. Clockwise is R, counterclockwise is S. So this is going to be R. All right. Questions about that? This is the most basic form that you'll find a chiral center in. It's just a simple tetrahedral like that. All right. And again, going back to our criteria for chirality, sp3 hybridized, non-symmetrical, 4 different groups attached, non-superimposable mirror images. So we already drew the mirror image, worked on that yesterday. I'm sorry, Monday. So the mirror images we already know is non-superimposable. What would the configuration be for the mirror image?
The opposite.
It has to be. Right, it has to be the opposite. Let me add to this. All right. So if you know the configuration of one stereoisomer, you can extrapolate from that what the configuration will be for the mirror image. you know one enantiomer, then by default, the other enantiomer has to be the opposite. So if this is R, the enantiomer of that will have to be S. All right, any questions about that? Now, let's go ahead and I'm gonna go ahead and we'll do the Fischer projection now, and then we'll come back to that one in the middle with the 3 stereocenters, because we want to talk about some other, another concept with that. We're gonna add in another concept. All right, no questions. Everybody's quiet today.
I have a question.
Mhm.
Is it not R, like the one we just did? Like, why did you redo it?
Redo it as in, what do you mean by that? Why did I turn it to show the steering wheel, to show the top 3 groups?
Yes,
Well,
because on the thing, the hydroxyl 1, the carbon double bond to the oxygen is 2, and so like on that is going counter, and then when you redid it,
right, that's why we had to do that. But even if you look, when we turn, let me see. I think it's mislabeled. If we turn the top around, OH is going to be where the 2 is. I think you're right. The OH should be here. Is that right? If we put an axis here and turn this way, shucks, sorry about that. Turn that way. Every group is going to rotate around. So the 1 is going to come here. I'm glad you caught that. The 2 is going to come here. And the 3 will stay vertical. You're right. And so the configuration should be S. It's counterclockwise. I mislabeled the 1 and 2 groups, but you can look at that example and see if you just rotate it around this way, the OH is going to come over where the cyanide is, and the aldehyde is going to come to where the OH is. Because you want that 4th group to be going back into the page away from it.
okay, thank you.
Thank you. Thanks for catching that. All right, let's move on to the Fischer projection, which is here. Fischer projections are a little bit different. You don't have to do any reorientation, but there's a rule for them. All right. Remember, I showed you the other day on a Fischer projection, if I drew this in 3D, these groups that are horizontal are actually wedged, and the groups that are vertical are actually dashed. Right, if I drew this in 3D, but sometimes you'll see the Fischer in 3D, but most times you won't, you'll see it in 2D. So let's look at the bottom stereocenter first, because that is the most straightforward. All we're doing is prioritizing first, and then we're going to count, right? And we'll talk about the rule for Fischer projections also. So out of the 3, so here's the chiral center right here, the 3 groups attached, 1, 2, well, 4 groups attached, 3, and then this carbon right here. Is that right?
Yes.
And it's that carbon and everything attached to it. Just in case we have to look for a second atom or move to the next atom to find a point of difference. All right, so let's look at that. And we know that hydrogen is going to be 4. Right? Let's look at between iodine, oxygen, and carbon, because those are the 3 groups that are attached directly to your chiral center. Which one is going to be highest priority?
Iodine.
Iodine, good. So we're going to call that 1. And then between oxygen and carbon, which one is going to be higher in priority?
The
Oxygen.
carbon.
Oxygen. Doesn't matter. I mentioned the stuff that's bound to that carbon on purpose. It doesn't matter. I'm looking at the first atom attached and comparing the atomic numbers. So oxygen is 2, and then that top group, the whole thing, but it's the carbon that's attached, is 3. All right. So now, since the hydrogen is vertical, so this is a Fischer projection. Or I'm going to put or four, right? Lowest priority. So if the fourth group, the lowest priority group is vertical, then what you see is what you get. You don't have to change anything. All right. So let me not just say H, because there can be other groups that are low priority. If the lowest priority group, come on, Russ, tighten up. We want to say up or down, doesn't matter, because if it was on the top carbon, it would be pointed up. If it's vertical, and once you prioritize, you're good. Right. So how are the groups oriented here? If we count it to three.
Clockwise.
Clockwise. Good. Because I'm going this way. 1, 2, 3. So that bottom stereocenter is R because the hydrogen is vertical. So we're going to leave that as it is. So this is R. Any questions about that? The process is the same. Prioritize, and then you look for the lowest priority group to see if it's vertical or if it's horizontal. All right. Let's do the top stereocenter. Somebody help me prioritize that. We're looking at this carbon right here now. It's got a bromine attached, it's got a carbon, it's got a hydrogen, and it's got another carbon down here. What's going to be one there?
Is it the bromine?
Bromine. Good. This is 1. And then between this carbon and this carbon, what do you think?
The one at the bottom.
Okay, why do you say that?
Because it's connected to iodine, hydrogen, and then the OH group.
Okay, it's connected to, and I agree with what you said, but I'm also looking at the fact that that top carbon is that's a carboxylic acid. So it actually looks like this, right? So it's here. So that's what's going to take precedence. So that double bond to oxygen in the top is going to cause that group to be higher in priority than the carbon on the bottom, which only has a single bond to oxygen. That's my point of difference. Oh, sure, sorry. Really, bro? Sorry. All right. So that top group has a double bond oxygen. So it's going to be higher in priority. All right. So we said bromine is 1. And then we said, or we're saying that the carboxylic acid is going to be 2. And that makes that bottom carbon 3. Is that right?
So I have a question.
Go ahead.
So
it's possible for Fischer projections to have two different configurations.
Oh, yeah.
Hmm.
You look at a sugar like glucose or sucrose in the anomeric form where it's open and not closed up into a ring. Yeah, all those stereocenters can be different.
Okay.
It's no different than having a molecule like this with a bunch of different carbons and all the carbons having something different attached to them.
Did you show like the whole thing when we're done, like how it look
What do you mean, like,
on the model, if you can?
you mean this one?
The one you've been using.
No, I'm saying you want to see the Fischer projection that we're looking at right now?
Yes.
Let me see. Let me put it together and I'll turn my camera on. Green. That's that. OH, H, and then up top. Gotta build this carbonyl right quick, so hold up. Hold up. Bromine. And I need a hydrogen. All right. So what are you not seeing in the top example? Or you just
I just wanted to see like the orientation, how it look.
so it would look like this, right? I mean, OHI. So this is OH, that's iodine, that's hydrogen. And up top, this is hydrogen. Hold up. I gotta swap that over so it'll look like what you're seeing on the paper. Yeah. So up top, there's hydrogen, bromine, and then the carboxylic acid back here.
Mm-hmm. Oh, okay.
All right. Now let's talk about the configuration because we prioritized it, but there's a rule for if the lowest priority group, which is 4, which is this hydrogen, is horizontal. If that lowest priority group is, I'm going to just quote everything up to that point. If it's horizontal, then you have to reverse the configuration. So if the lowest priority group, I put that in quotes now, so don't panic when you see that once I post the notes. If the lowest priority group is horizontal, then you have to reverse the configuration. So instead of, so let's count it up. Let's count 2, 3. So we said bromine is 1, and then the carboxylic acid is 2, and then the other carbon at the bottom is 3. So which way is that? Right now, if I just count it, it's actually what? S?
Yes, yes.
It's S. But since the hydrogen is horizontal, I have to call it R. Right? Because again, if you look at the model, with the hydrogen being, which one is right here? Horizontal. Can you see that? Let me get this right here in this camera. Can you see how that's coming out at you? and not coming back to me, towards me?
Yes.
Yeah. So the fact that H is coming out means that once I have prioritized, it's going to have the opposite of what I see, because the goal is always to get that lowest priority group away from you when you're doing the configuration or determining configuration. This background sucks. I need a green screen to keep the back, like what's behind me, from bleeding into the camera. All right. So that's going to be actually R. So what is the configuration overall? It is what?
S.
It's RR. Because the bottom we said was R,
Mhm.
and now the top is R. Is that right?
Yeah.
So it's RR. So that leads us into another concept. Let me add another page here. That leads us into another concept, which is the concept of diastereomers. So a diastereomer is a type of stereoisomer, but it's not a mirror image. All right, let's take that Fischer projection, and I'm just going to redraw it. This was bromine, this was hydrogen, this was an acid, this was iodine, hydrogen, and OH. Is that right? And we said that it's RR. Correct?
Yeah.
What does the mirror image look like?
Bromine and iodine are on the left side.
Okay, because it's looking at itself in the mirror. Is that right?
Mhm.
H, OH, CO2H. Is that right? And then H here. Yes.
Uh-huh.
Now,
Yeah.
what is the configuration of the stereocenters in the mirror image?
The opposite.
It's got to be the opposite. So this is going to be what? S, and that's going to be what? S. Is that right?
Yes.
I'm gonna call it what the proper name for it is. An enantiomer. Are we okay with that? We're clear about that?
So the diastereomers, is that how you say it? It's not a mirror image, so
Right. We haven't gotten to that yet. We're gonna get to it right now.
oh,
I'm setting it up because we know what the mirror image looks like, but the question is, how many stereoisomers are possible for that compound? How do we know that? Anybody?
Can you repeat the question?
How many stereoisomers are possible? It's 2 to the n, right?
would it be 2 to the first? I don't know.
How many stereocenters are here?
Oh,
2.
2.
2. So it's going to be 2 to the 2, which is 4. All right, let me make that clear. That n, that's the number of chiral centers, right? It's the number of chiral centers. So n is the number of chiral centers, 2 to the n is the number of stereoisomers possible. So we got 4. So the other 2 have to be something. They're not enantiomers of the first one because that can only have one mirror image. And so for the other 2, what you have to do is draw, let me show you. I'm going to keep this one how it is. And on the bottom, I'm going to change that. right? Did you catch that? I changed this stereo center right here, but I left the top one as is. So for a diastereomer, you're only changing one stereo center. For the enantiomer, you got to change all of them. So whatever the configurations are in the initial isomer, which was RR, for the enantiomer, everything changes because it's the mirror image. So it's not a mirror image. And you must have at least two stereocenters in order for diastereomers to be possible. Right? You got to have a minimum of two. If you only have one chiral center, you cannot make diastereomers. You can only make the mirror image. But if you got two or more chiral centers, then you can have what's called a diastereomer. So this will be a what we call a diastereomer. All right, we know the top. We didn't touch that, so we know that's R. Is that right? Yes, no?
Yes.
Because we've already determined that. What is the bottom?
The
Since we
opposite.
altered it.
Would be the opposite.
So it is what? S. Following? So in the diastereomer, you're only changing one stereo center at a time, right? So it's not a mirror image, but it is a stereoisomer. Still a stereoisomer. All right,
I have a question.
go ahead.
Can you repeat why we have to change one of them?
If you change them both, it's an enantiomer. If you don't change anything, it's the original.
Oh, okay. Okay.
All right, so that's one. We said that there are a total of 4 stereoisomers possible. What does the other one look like?
Change the top one, leave the bottom one like the original.
Okay, change the top one and leave the bottom one. Okay, let's do that. Let me get them. So we're going to say that the top, we're going to do ER over here, H over here. That stays the same. And then I want to go back to the original on the bottom, right? So the bottom we know is R, because that doesn't change. And then the top we're going to say is S. Is that right?
Yes.
So those are my 2 diastereomers for a total of 4 stereoisomers. What's the relationship between the 2 diastereomers? Look at the configuration of the first one and compare it to the second one.
Are they enantiomers of each other?
Of each other, yes. These 2 diastereomers are enantiomers of each other. All right. But this is also a diastereomer of the original. Let me get my handwriting together. All right. But when you compare the 2 diastereomers to each other, they are enantiomers of each other, not of the original image. All right. Questions about that? Let's do this last one because it has 3 stereocenters. So what does that mean? How many stereoisomers are possible?
8.
8. Good. What do you think? Not knowing what you know now, what do you think those 8 are going to be composed of? Like what you're going to have some enantiomers mixed in with what? Some diastereomers. Yeah. All right. So first, let's go through this one and figure out the configuration of each one. Let's start with this one. And the reason we're going to start here is because H is already pointed back. So we don't have to reorient. We don't have to do anything. On these, the H is coming forward. All right, so let's start with that first one. What are my four groups? So again, we combining all the skills that we've done so far. We're identifying the chiral center. We're going to prioritize it, and we're going to determine its configuration. And then eventually we're going to draw the mirror image and then draw the other isomers. All right. What is the priority? How do we prioritize that chiral center that's highlighted in yellow? Where are the four groups?
The chlorine
Okay, that's one. Good.
and
That
The
carbon
carbon.
over here. Is that right?
and then the carbon to the left.
This carbon and then the hydrogen.
Mhm.
Is that right?
Mhm.
So now we need to prioritize. What's number one? What's the highest priority group?
Chlorine.
Chlorine. Compare, because you compare chlorine to carbon in each case, right? So that's one. We know H is going to be 4. The only thing lower than hydrogen is a lone pair. That's the only thing that's lower in priority than hydrogen is a lone pair. All right, hydrogen is always going to be your lowest priority group unless it's on the same atom with a lone pair. All right, what's 2? You got 2 choices. You got a CH3 over here. Let me write that in. This is a CH3. And then you have a carbon here bonded to oxygen. What do you think?
The one bonded to oxygen.
Good. So that's going to be 2, making this by default 3. Is that right? What is the configuration? All right. All I have to do is count to 3.
S.
S, because when I count to 3, I'm counting this way. All right, so that stereocenter is S. Any questions about that? All right, look at the second one and somebody prioritize that. Let's find the groups first. Always find the 4 groups, then prioritize, and then assign configuration. So this is a group, is that right?
Mm.
This is a group. Yeah.
Yes.
And then this is a group. And of course, the hydrogen is a group. Now we need to prioritize it. Which group is going to be highest?
O8.
The O8, the oxygen. So this is going to be 1. And then between this carbon over here and this carbon over here, which one do you think is 2? This is kind of
The
tricky.
one,
Oxygen.
All right, let's think about it. On the atom to the left, it's bonded to a carbon. Is that right?
Yeah.
The atom on the right is bonded to what?
chlorine,
Chlorine.
Oh,
Which one is higher in priority?
the chlorine.
Yes.
chlorine,
Yes. So this is going to, on that side, this is going to be, so that's 1. And then this group over here is going to be 2. And then by default, that makes this group over here 3. Is that right?
Mhm.
So we prioritized it. If we counted to 3, it would be clockwise, wouldn't it? Is that
Yes.
clockwise?
Yeah.
However, the 4th group, which is the hydrogen, is not away from us. So we can apply the same rule to this like we apply to the Fischer projection. And that is, if the 4th group is on a wedge, we just reverse what we see. So instead of it being R, we're going to call it S because the 4th group is on a wedge. Following?
Yes.
The lowest priority group is not on a dash. That's just a shortcut that we can use. Let's do the last one and then we got to stop. So let's do this one right here. What are the groups attached to that?
The carbon at the bottom.
Okay. Carbon right here, is that right?
Mm-hmm.
And a carbon right here on this right side. And the hydrogen, good. And we know that hydrogen is 4, right?
Yes.
Let me pick a different color pen, sorry. Come on, pen, tighten up. Already, it's red. It's orange. So we know that's 4. Which of those groups, which is going to be 1? All of them are carbons. So you have to find a point of difference.
The one at the bottom.
So you have the carbon here at the bottom is double bonded to oxygen. The carbon over here has a single bond to oxygen. Is that right? So this is going to be 1, this is going to be 2, and that's going to be 3. So how would I count that? Is that clockwise or counterclockwise? Looks like it's counter, doesn't it? If I count from 1 to 2 to 3, that's going to be counterclockwise. Yes?
Yeah.
So it's S. But what's the rule again? If the H or the lowest priority group is wedged, we have to reverse it. Right? So even though it says it's S, then that it literally is R because the H is pointed out at us. So the configuration, let me see if I can paste this again real quick, is, what did we say the first one was? S. And then we said this one was R. And then this is S. Is that right?
Yes.
No, it's not. No, it's not. The middle one is S. And the last one is R. My bad. This is S, R. So what I want you to do before you come back on Friday is, and we can talk about it right at the beginning because we're going to start another topic Friday. I want you to give the configuration of the enantiomer and draw 2 diastereomers. All right. And then on Friday, we'll start out with that, and then I'm gonna send you another video for the next topic, which we'll start on Friday. All right. This is all this here is practice, reps, reps, reps. So look in the syllabus, look at the practice problems that are there, and then try a few of them. All right. We'll talk again on Friday, God willing. And yeah, if you didn't put your name in the chat, make sure you do so before you sign out.
You have a good day.
All
Have a
right.
good day.
All right, y'all take care. Thank you.
Thank you.
All right.